Hey guys, welcome. Yeah, so part 5 here, and what we have to do is find the volume of the solid bounded by the xy plane, so this gray plane here, and the paraboloid, this orange surface, given by z equals 2 minus x squared minus y squared. Cool. All right. We now know that we have to start with a double integral of zda. And so z is right here, and then we've got dA, double integral, over region D. And our region D here is going to be the circular bottom of our solid, right? And the circular bottom of our solid is where the xy plane meets our paraboloid. And since the xy plane is where z is equal to 0, to find the circular bottom of our solid, what we need to do is set z to equal 0. Right? And again, that's because our paraboloid meets the xy plane at the circular bottom, and the xy plane is when z is equal to 0. So if we set z equal to 0 here, we can turn this equation to read, once z is equal to 0, we can get it to read x squared plus y squared is equal to 2, which means that this circular bottom here has boundary given by x squared plus y squared equals 2, so it's a circle. The boundary here down at the bottom of our solid is a circle with a radius of root 2 and centered at 0, 0 in the xy plane. Okay, cool. But that means that the inner limit of integration for this first integral will have to involve the bottom half and the top half of a circle. And the circle, of course, being x squared plus y squared is equal to 2. So if we choose dA to be, let's say, dx dy, then the limits of integration here would have to be negative the square root of 2 minus y squared and positive the square root of 2 minus y squared. And that's, again, if we choose dA to be dx dy. But we do not like that. That's complicated, right? So what that's telling us is, since doing our double integral here in rectangular coordinates seems really ugly, we should switch coordinates. And so what we're going to do is change to polar coordinates. Now, in polar coordinates, I want to emphasize that dA is r times dr times d theta. You might be tempted to think that dA in polar coordinates should be dr d theta, but it's not. It's r times dr times d theta. And so in a separate video, a very short video, I explain why that r has to be multiplying dr and d theta when we switch to polar coordinates and interpret dA in polar coordinates. Yeah, we have to have that r multiplying dr and d theta, and I explain why in a different video. I also explain why that's got to be in my video on the Gaussian integral, so check that out if you'd like. But yeah, okay, so dA here we're going to replace with r dr d theta, and here I'm gonna group x squared and y squared, so write 2 minus a quantity x squared plus y squared. And then of course if I write r dr d theta for dA, the limits of integration for r are going to go from 0 to root 2 because our circle has radius root 2, and the outer limits will go from 0 to 2 pi, that is go all the way around. So yeah, if we go radially out to root 2 and go all the way around, then we've captured our circle in polar coordinates. Yeah, okay, so writing everything I just said will mean that we write this here. Okay, cool. Now we want to do something about this x squared plus y squared, because that puts us still in rectangular coordinates. So a quick refresher of what x squared plus y squared in polar coordinates would have to be would start with this move and end with this move. You should have learned this in pre-calculus, and so I'm not going to explain it in detail, but yeah, in polar coordinates, x squared plus y squared will have to equal r squared through the sequence of moves here. Yeah, okay, cool. So that means our integral, our double integral, is now this, and I'm intentionally highlighting this here, r dr d theta, so you know that that r is there, because yeah, now we've got a bunch of r's here. Well, we've got another r here. I don't want you to be confused and forget about that r. That's crucial right there. Yeah, okay, cool. Now if we distribute that r in, then we can write this here, right? And now it's just a matter of like doing this double integral, which is pretty straightforward. We integrate with respect to r first and evaluate, and if we do both, which is integrate and evaluate, this 2r integrated would become, once we take the antiderivative, would become r squared, and then we'd have minus r to the fourth divided by 4 evaluated from 0 to 2 would get us this here. And then we'd just have this here times d theta, integral from 0 to 2 pi. Yeah, now root 2 squared is 2, and root 2 to the fourth is 4. So we have here 2 minus 4 over 4, but that's just 1. So we just have left 1 d theta. So what would have been a very difficult integral to deal with in rectangular coordinates has become a very simple integral to do in polar coordinates. And so there we are, and so here it is. And to conclude, you just integrate 1 d theta, which is theta evaluated from 0 to 2 pi, which is 2 pi. Yeah, cool. So that means that the volume of this solid right here is 2 pi. Neat. Keep watching. Hope you enjoyed this. Take care.